Thanks everybody else for joining us today. I'm Steve DeStassi, an electrical engineer for Parker Lord. I've been working here 14 years designing wireless sensors that get used for structural, machine, and environmental monitoring applications.
Hey everyone, my name is Jody Dunkley and I'm a field applications with Parker Lord. I've been with the company for 7 years. I started in the wireless system product development team as a test engineer and now have the pleasure of helping customers design and deploy sensing systems to solve their unique real-world challenges and innovations.
In addition to wireless sensors, our group here in Vermont designs and manufactures precision displacement sensors and also small high-performance inertial measurement devices that are used for navigation and position sensing.
Our wireless sensing systems are used extensively for test and measurement applications, long-term environmental and process monitoring, and condition-based and usage monitoring for diverse industries.
So one of our customers, Beta Technologies, who's right here in Vermont, has given us permission to talk about their application. And it's a really exciting application where they're developing a fully electric aircraft, and they're using a pretty large number of our wireless sensors to help them do it. Jody's been working with these guys for a while now, and she knows all about this application. Jody, can you tell us about this aircraft that they're building?
Yes, I can. Working with Beta has been a really great project. It's fast-paced development and they're working to be one of the first to complete design of this type of aircraft. Vertical takeoff and landing aircraft have been around for a while, but an all-electric version is brand new technology. They have many challenges to work through, including the weight and safety of the batteries, the design of the propulsion system, and the airframe itself.
That's pretty exciting. And they're developing the whole aircraft, right? Not just pieces of it?
Yeah, that's right. Today we're going to talk about the prototype that was built using an existing airframe. Currently, they're working on building it from the ground up, not only to control all flight characteristics, but also for customization for their first customer use, delivering organs for transplant operations.
So something we hear over and over again from our customers is about how critical the data is, and likewise how expensive and costly it is to not get data when it's needed, especially in the case of an aircraft where the amount of preparation for a test can be tremendous, not to mention scheduling that can go into these tests. And in some cases, such as this extreme example with the picture of vehicle crash testing, the test can be destructive. There might only be one chance to collect the data that's needed without a pretty significant detriment to the timeline or budget.
This is especially true in these investigative test and measurement applications, where customers are using sensors to iterate design concepts. Small modifications to the design require reliable and consistent data acquisition. And in dynamic, fast-paced development teams like Beta's, many tests are being conducted each day. The faster and easier sensor instrumentation can be added on, the more confidently they can compare theoretical and actual performance.
At this time, we're going to launch our first poll question, which is on the topic of sensor data. We're trying to get a better idea of who's in the audience, and we're going to end up letting you guys all know the results of these polls. So the first question, what application are you using sensors on? Test and measurement, condition-based monitoring, process automation, or other? And if it's other, just throw your answer into the chat window and hit enter.
This is the proof of concept piloted aircraft weighing about 4,000 pounds with a 35-foot wingspan. Target speeds are 154 knots with a range of 150 miles. It was built on a conventional airframe, adding the 4 boom assemblies to hold paired counter-rotating propellers that are used for lift and vertical takeoff. It is powered entirely by batteries and uses 8 124 horsepower electric motors to spin the propellers. It's nearly a ton of lithium-ion batteries. Each motor and rotor can be controlled independently, and the combination of them is used to change lift and steering dynamics. In this version, once at elevation, the propellers tilt as the aircraft transitions into traditional flying mode. One of the key things they learned from this prototype was the tilt feature was complicated and maybe not necessary for a revision in which they could emphasize other design characteristics. This test aircraft achieved 72 knots, 100 feet elevation, and over 180 test flights approved by the FAA.
In the next 4 slides, we're going to be showing where and how our wireless sensors are being used for testing this prototype aircraft. A quick summary on the left is showing that we'll be testing vibration, strains and loads, temperatures, and we're also measuring orientation of the aircraft using our GNSS-aided inertial measurement unit, which is reporting aircraft orientation right into the nav system.
So this is a close-up of one of the 4 rotor propeller assemblies installed on the aircraft. Before this design could be flown, test and analysis was required. It's kind of similar to Whirl Tower used in helicopter testing. And in this case, Beta made a mast to attach propellers to in order to understand the aerodynamics of various propeller designs. They installed a load cell at the base of the mast and spun it through the range of propeller speeds up to 1200 RPM, measuring the tension on the load cell to correlate it with thrust. They also put 2 accelerometers to measure vibration and balance characteristics, and a tachometer was used to mark blade revolutions. Finally, a dozen strain gauges installed on the top and bottom of each blade measured stretching from centrifugal and bending loads in the range of 10 to 20,000 pounds.
So just to summarize, they're using multiple V-Link 200s, which is our 8-channel wireless sensors down there on the bottom left, attached to strain gauges, load cells, and a tachometer. They're using 2 of our G-Link 200s, which is our wireless accelerometer, pictured next to the V-Link, for monitoring vibration. And because they're using a network of these devices and all the data is synchronized, they're actually able to sync up all these strains and loads and vibration waveforms directly with the blade location, which is really cool. Jody, what are they actually determining from all this data they're collecting?
Well, from the testing, they were able to try out as many propeller designs as they could come up with, and know that once it was installed, it would be structurally sound enough to bear the loads they would see in use and produce enough thrust to overcome the anticipated weight of the aircraft. What you're looking at here is the boom assembly without the airframe and the propellers. This test is similar to the test stand monitoring in that it used the V-Link analog voltage node with strain gauges and a load cell, but in this case they used a hydraulic press to apply expected loads to the boom structures and then measure dynamic strain at critical points of structural integrity. This test was repeated through the range of boom positions that emulate conditions in flight. So you can see there's quite a few V-Links there lined up at the bottom, and they're connected to strain gauges along surfaces of the boom assembly. And each location is measuring critical points of structural integrity on the boom.
Up front there, you can see the weight that's hanging, right? And it's kind of mounted in the middle point there, and then the weights are hanging off the end.
It's actually a hydraulic press, and they're pulling on the end of the boom, and then they might rotate the boom assembly in the fixture that it's on, and then a pull on it in it from a different direction. As I mentioned, the propeller boom tilts during the different flight transitions, so they wanted to make sure they tested it at each angle.
Yeah, so they're essentially putting weights on the end to simulate an amount of load on the end that correlates to a very specific event that could happen in flight.
That's right. I mean, plus the mass of the propeller and the motor and all of the other components that you're not seeing here, but will be in the final aircraft.
So this test is being done in the lab. Do they actually repeat this outside on the full aircraft?
Yeah, they did in-flight testing as well with strain gauges in the same or similar locations, and they're able to collect the same data and confirm testing that they had done in the lab as well.
These guys are monitoring temperature on their lithium-ion battery packs using our TC-Link 200s. The TC-Link 200s are a 12-channel thermocouple temperature sensing device. They make measuring temperature from thermocouples really easy. You just tell the device what type of thermocouple it is. They handle all the calibration and cold junction compensation and just give you temperature. Jody, I've got to imagine a battery used for flying an aircraft has got to be pretty big and potentially dangerous.
Yep, about 1,500 pounds of lithium-ion battery packs with 124 kilowatt hours of capacity. That's a lot of batteries to worry about. lithium-ion batteries can be induced into thermal runaway and catch fire at about 70 degrees C. And to get all that capacity they required, they needed 6 separate packs, each having multiple cells, and they were distributed around the aircraft. So to monitor this risk, they installed temperature probes, the thermocouples you mentioned, into the pack assemblies to make sure the battery temperatures stayed in a safe range during all the operations. In the prototype, this was up to and during the peak hover power of about 500 kilowatts, which was sustained for 8 minutes.
What's actually the most dangerous situations for these batteries on the aircraft?
Well, during normal operation, I think that charging the batteries at the launch pads is actually the most dangerous, but peak draw is definitely during hover mode. Eventually, as they prepare to go through FAA certification, I expect they'll also have to characterize what happens with the batteries in the case of a catastrophic event.
This is a really good example of the destructive testing we talked about earlier when we were talking about the value of good data. In order to test the limits of a lithium-ion battery, you need to push it past its limit. A pretty destructive event, or it can be. You don't want to perform a test like this and then look back on it and realize you didn't get the data you need.
So all aircrafts, including this one, have natural resonant frequencies associated with their airframe design and structures. It's really important to understand these frequencies because if they are left to oscillate there, it could result in significant structural damage or make the aircraft unflyable. Another concern in aircraft design is understanding in-flight aerodynamically induced vibration, such as conditions that would lead to flutter in the tail. All of these concerns make high-resolution, full waveform vibration monitoring key in airframe design.
For this testing, they used our G-Link 200, which is our ruggedized, weather-rated 3-axis wireless accelerometer. It's great for measuring motion and vibration. And in cases like this, where we're looking at a bandwidth of DC up to 1,000 hertz, it can also be used to report what we call derived channels, which is vibration metrics such as velocity, peak-to-peak magnitudes, and crest factor. So what makes it work for this application really well is that you can have a network of them, and they're all synchronized. So any events that happen at a certain location, you can see how that propagates through the aircraft.
Yeah, and I also mentioned that using the derived channels reduces your data use as well. So instead of, if you only need peak data or RMS data, you can have just that information sent instead of the full waveform, which can be very beneficial for saving batteries too.
If you look to the right on this image, you can see some of our software. We've got a couple different types of software that our customers use. One is Sensor Connect, which is PC-based. Another is Sensor Cloud, which is a cloud-based software package, so you can look at your data from anywhere in the world.
And for this application, one of the great features of both of those software pieces is the ability to do FFTs and pull statistics out of the data.
What Jody was describing, where you guys have probably seen the videos where you get helicopters that, essentially start shaking themselves apart. This is testing essentially in order to make sure the aircraft doesn't do that. To make sure all the parts on board are not vibrating at the same frequencies that their structural frame is resonant to.
At this time, we're going to launch our second poll question. We've been talking a lot about this one particular aerospace application, but as we've said before, our sensors can be used in a lot of different ways. So we'd like to know, when we get into our Q&A, where you're all coming from and how sensing could help your applications. So what industries do you represent? Oil and gas, aerospace, off-highway, environmental, industrial, or other? And if other, let us know in the chat, please.
So we've told you a lot about Beta Technologies' application, testing an aircraft, but our devices are being used for so many applications. We've got a couple of them pictured here on the right where we've got off-highway vehicles, we've got bridges, roller coasters, where our devices get used for monitoring vibrations, strains, temperatures, in so many different ways. And the reason our devices are being used in so many different ways is that they're adaptable. We've got different wireless sensors to meet the needs of different types of sensing, and we've got different ways of using them. For instance, we've got different operation modes. You can run our devices continuously. You can run them periodically. If you're looking for trending behavior for something like a vibrating bearing or a gear that's going to slowly degrade over time. Or you could trigger off of events and just get that data that you're most interested in. Okay, there's also a variety of ways to present the data. We mentioned a few of them before. Sensor Connect is for looking at data on your PC. Sensor Cloud is a cloud-based service where our devices can push data right onto a network so you can view it anywhere in the world. You can put algorithms up there. You can automatically push alerts to your cell phone or email in the case of events happening. And then we also have MSCL, which is an API that you can use for developing our wireless sensors directly into your own software.
Yeah, some of the most interesting applications are when customers integrate our sensing systems into their own bigger projects. So with our open source communication library, customers can write their own code and basically port the data into their own data acquisition system and combine it with other data that they might want to look at. And this has been really effective and interesting in like process monitoring applications where they want to see multiple parameters from equipment they already have that provide some data, and then they just want to add on, wireless for measuring things that are a little more difficult, or they want to add on afterwards.
Yeah, in a lot of cases, people end up using our wireless sensors to characterize a mechanical system. And then once they've done that characterization, they're able to then use our wireless sensors deployed full-time to help in a different mode of operation to help predict the health of that machine. At this time, we're going to launch our last poll question. The question is, have you used a wireless sensing system before? Yes or no?
So while we wait on the responses from the poll, I'd like to hit on some of the points of why wireless can be a big advantage over wired systems. The bottom line is it saves time and money, and how it does that is by enabling fast and consistent instrumentation that can be used during design and development cycles and make retrofitting existing installations faster without having to worry about running wires or maintaining wires. Wireless sensors can be used where wireless systems cannot, such as rotating parts or articulating arms, and replace other unreliable methods such as slip rings. Lastly, for some applications, digitizing the signals at the measurement source and removing the need to run long wires will improve noise immunity or susceptibility to EMI. There are several types of wireless systems, and we have optimized ours for specific kinds of uses. Our wireless system is optimized for high-resolution data acquisition across time-synchronized sensor channels with features that guarantee data will get through. So reliability, time synchronization, and high resolution are kind of the key components of our particular wireless system. There's flexible data acquisition and visualization options, as Steve talked about, including local reporting, some analysis tools, cloud reporting, and the open source integration tools. The systems are highly configurable and can be used for diverse test and measurement applications to fuel technology innovation or long-term process and condition monitoring to improve efficiency.
Okay, regarding reliability, all of our products have a strict qualification process which they go through. This includes some pretty rigorous environmental testing, temperature cycling, vibration testing on the shaker table, accelerated life testing in the Halt chamber, water submersion for our IP67 rated products such as the G-Link and also the SG-Link 200, EMI and EMC testing. In addition to the qualification testing, every one of our products that we build here gets individually calibrated, tested, and is tested for performance over temperature as well.
Well, one of my favorite things when I was a test engineer was figuring out how to break our products. It was all in order to make the design better, but it was definitely one of the funnest parts.
I do remember Jody used to have fun with some of the, especially the Halt chamber testing. She'd put little flags on the devices that would wave back and forth as the products were getting vibrated, and slow-mo videos of the ESD testing, the products getting electrocuted. Thanks everyone for listening to us today. Before we get into the question and answers, I just want to highlight a couple key takeaways from this talk. First one being, if you can collect data accurately and repeatedly, it allows you to make iterative changes to a mechanical design, such as with Beta's aircraft, where each change that they make can be tested and they can understand how that change is affecting the whole system. Wireless sensors speed this up because of how quickly they can be deployed, how versatile they are for different applications. They can be moved around in different environments really easily. They can save a lot of time over traditional wired DACs. Lastly, our wireless sensors give you the opportunity to characterize the mechanical system and then leave them on there to do some long-term monitoring of the health of these parts.
So thanks everyone for attending, and we're happy to answer questions you might have. And that goes for right now and anytime. I'm always excited to hear about new customer applications and ideas.
Thanks again, everybody, for joining us today. Go to www.microstrain.com to learn more about our wireless sensors. Give a call if you have an application that you think our wireless sensors might help with. You get to talk with Jody and our other awesome support team here. So now we're going to open it up for questions and answers.